February 9th, 1944. The frozen coast of Normandy, France. Oberst Heinrich Kästner stood in ankle-deep mud, watching Organisation TOT workers pour concrete into massive wooden forms. The bunker taking shape before him represented 6 weeks of brutal labour, 60 cubic metres of reinforced concrete, 22 tons of steel reinforcement, 2 metres of protection capable of withstanding direct hits from Allied naval guns. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Around him stretched the Atlantic Wall, Adolf Hitler's fortress Europe. From Norway to Spain, 25,000 concrete bunkers guarded 5,000 kilometers of coastline. Each structure required skilled engineers, specialized equipment, and weeks of construction time. The Germans had transformed defensive architecture into an industrial art form, creating standardized designs catalogued in thick volumes of Regelbau specifications, but Kästner had seen the intelligence reports. Across the English Channel, the Americans were massing for invasion, and when they came, they would bring something the German military had not anticipated. Not a weapon, not a new tank or aircraft, something simpler and far more revolutionary: the ability to erect functional shelters faster than Germany could aim its guns. The story of why American Quonset huts could be assembled in a single day while German bunkers required 6 weeks reveals more than comparative construction speeds. It exposes two fundamentally opposed philosophies of warfare. German strategy emphasized permanence, protection, and prepared defensive positions. American doctrine prioritized speed, mobility, and the rapid projection of force across vast distances. One nation built fortresses meant to last decades. The other built temporary shelters designed to be obsolete within months. By 1944, this philosophical difference had become a matter of survival. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The German approach to military construction had deep historical roots. Fortress engineering had dominated European warfare for centuries. From medieval castles to the elaborate fortifications of Vauban, European military thinking emphasized the defensive power of well-constructed positions. A properly fortified location could allow a small force to hold against a much larger army indefinitely. This tradition reached its apex in the interwar period with the construction of the Maginot Line. France spent the equivalent of billions of dollars creating an interconnected system of underground fortresses along the German border. Massive gun turrets rose from reinforced concrete bunkers. Troops lived in underground barracks with electric lighting, ventilation systems, and ammunition storage. The Maginot Line represented the ultimate expression of defensive fortification. Germany watched and learned. Though they had been forbidden from building fortifications under the Treaty of Versailles, German military planners studied French methods. When Hitler repudiated the treaty in 1936, Germany immediately began construction of its own defensive line. The Siegfried Line, called the West Wall in German, stretched along the western border facing France. German fortress engineers developed the Regelbau system starting in 1933. The term meant standardized construction. Rather than designing each bunker individually, engineers created a library of approved designs. Each Regelbau type received a specific designation number indicating its purpose and specifications. Type 501 was a standard personnel bunker. Type 677 housed anti-tank guns. Type 669 protected coastal. Artillery. The advantages of standardization were numerous. Proven designs could be replicated with confidence. Industrial manufacturers could produce identical components in quantity. Armor plates, ventilation systems, and steel doors used the same specifications across hundreds of bunkers. Engineering officers could survey a location and select the appropriate Regelbau type from their reference manuals. But standardization came with significant complexity. Each Regelbau design specified exact construction methods, material requirements, and building strengths. The Germans categorized bunkers into 3 construction classes: ständig, meaning permanent, featured walls and ceilings between 1.5 and 3.5 meters thick. Verstärkt Feldmäßig, reinforced field construction, used 1 meter thickness. Feldmäßig, field construction, employed lighter protection for temporary positions. The most common Atlantic wall bunkers used Baustärke B construction strength. This designation required ceiling and wall dimensions of minimum 2 meters with floors of 80 centimeters thickness. Such construction could withstand direct hits from half-ton aerial bombs on the roof or impacts from 220mm artillery shells. For locations requiring even greater protection, Baustärke, a construction increased wall and ceiling thickness to 3.5 meters, capable of resisting the heaviest artillery and 1,000-kilogram bombs. Construction of a standard German bunker followed precise procedures. First, engineers surveyed the location and selected the appropriate Regelbau design for the tactical situation. They calculated fields of fire, sight lines to potential landing beaches, and integration with neighboring defensive positions. The chosen location determined whether the bunker would be built into a hillside, dug into flat ground, or constructed on pilings. Excavation crews then dug the foundation pit. For a medium-sized personnel bunker, this meant moving dozens of cubic meters of earth. In coastal areas with high water tables, workers constantly pumped seawater from the excavation. In rocky terrain, explosives broke up bedrock. The foundation floor received an initial layer of concrete, typically 80 centimeters thick, reinforced with steel rebar laid in a precise grid pattern. While the foundation cured, carpenters constructed massive wooden formwork for the walls and ceiling. These forms had to be absolutely precise, matching the dimensions specified in the Regelbau plans. The interior formwork created the living spaces, corridors, and ammunition storage rooms. The exterior formwork shaped the outer walls. Between them, steel workers installed reinforcement cages. Heavy rebar ran vertically and horizontally through the wall sections, tied together at precise intervals. Concrete mixing began only when all formwork and reinforcement stood ready. The Germans initially imported cement, sand, and aggregate from as far as Poland and eastern Germany. Quality control was critical. The concrete mixture had to achieve specified strength ratings after curing. Inspectors tested samples from each batch. Pouring proceeded in carefully planned stages. Workers filled the forms layer by layer, allowing each section to partially set before adding more. Concrete crews worked around the clock when weather permitted. For a standard bunker, the initial pour might take several days. Then came the waiting. Concrete gains strength through a chemical process called hydration. Water reacts with cement to form crystals that bind aggregate into solid mass. This process requires time. After 24 hours, concrete hardens enough to support foot traffic. After 7 days, it reaches approximately 70% of final strength. Only after 28 days does concrete achieve its full rated capacity. German construction schedules accommodated these curing requirements. A bunker could not be completed until its concrete had properly hardened. During winter months, cold temperatures dramatically slowed the curing process. Concrete exposed to freezing temperatures before proper curing could suffer permanent damage, creating structural weaknesses that would compromise the entire bunker. While concrete cured, other work continued. Electricians installed lighting systems and communication lines. Ventilation specialists fitted the elaborate air filtration equipment required for chemical warfare protection. Every habitable bunker needed a ventilation system capable of providing 1.3 cubic meters of clean air per minute for each occupant. Manual pumps allowed soldiers to maintain air circulation, even if electrical power failed. The entrance system required particular attention. Nearly all German bunkers featured a gas lock, a small chamber just inside the entrance where personnel waited while overpressure from the ventilation system replaced potentially contaminated air. The main entrance door consisted of 2 sections of 3 centimeter thick armored steel. Near the entrance, a firing slit covered by an armored plate allowed defenders to shoot along the exterior walls, protecting against infantry attempting to approach the entrance. Once the concrete had cured sufficiently, crews removed the wooden formwork and completed interior finishing. Walls received wooden paneling or insulation to combat cold and dampness. 3-tier bunks bolted to the walls provided sleeping accommodations. Each soldier received approximately 2 square meters of living space. Metal lockers held equipment and personal items. A gas-tight, pressure-tight iron stove provided heating and had a hot plate for warming food. For gun emplacements, installation of the weapon system began only after structural completion. Large coastal artillery pieces required elaborate mounting systems embedded in the concrete. Ammunition hoists connected underground storage rooms to the gun positions. Fire control equipment linked the battery to observation posts. The timeline for completing a standard German bunker stretched across weeks. A small infantry bunker of the 500 series required approximately 4 to 6 weeks from initial excavation to final occupancy. Medium coastal artillery casemates needed 2 to 3 months. Large fortified structures took even longer. In 1942, when Hitler issued Führer Directive No. 40 ordering creation of the Atlantic Wall, Organisation Todt faced a staggering challenge. The directive called for 15,000 concrete structures along the coast between the Scheldt River and the Loire River alone. By the end of 1943, only 8,000 had been completed. Construction was falling behind despite employing 500,000 workers at peak. The mathematics were unforgiving. If a standard bunker required 6 weeks to build, and if Organisation Todt had sufficient materials and labour for 100 simultaneous construction sites, they could complete approximately 850 bunkers per year at each location. To reach 15,000 structures, they needed nearly 2 years of continuous construction. Field Marshal Gerd von Rundstedt, commander of German forces in the West, recognized the problem. In his situation report to Hitler in October 1943, he noted that the Atlantic Wall remained dangerously incomplete. Fortifications concentrated around major ports, but left long stretches of coastline inadequately defended. When Field Marshal Erwin Rommel arrived as inspector of the Atlantic Wall in November 1943, he found the defences woefully inadequate. Rommel had experienced Allied air power in North Africa. He understood that static fortifications alone could not stop a determined invasion backed by overwhelming air superiority. He argued that the war would be won or lost on the beaches. Germany needed to destroy Allied forces while they struggled in. The surf, vulnerable and disorganized. Rommel pushed for accelerated construction. In the first 4 months of 1944, Organisation Todt erected over 4,600 new fortifications. Monthly concrete usage doubled from 357,000 cubic meters to 722,100 cubic meters. This represented a remarkable increase in construction tempo. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Yet even this acceleration could not overcome the fundamental limitation. German bunkers required time. Concrete needed weeks to cure. Skilled labour was increasingly scarce, as the Wehrmacht drafted men for the Eastern Front. Steel and cement competed with tank and aircraft production for limited resources. Every bunker completed meant resources diverted from offensive weapons. Meanwhile, across the English Channel, American industrial philosophy was moving in precisely the opposite direction. The United States had no tradition of permanent fortifications. American military experience emphasized mobility and rapid force projection. From the westward expansion across the continent to the Spanish-American War in the Caribbean and Philippines, American forces had operated at the end of extended supply lines in territories without existing infrastructure. This experience shaped American thinking about military construction. Permanent fortifications made sense only if you intended to stay in one location indefinitely. But American strategy in World War II called for constant movement, island hopping across the Pacific, amphibious assaults against defended beaches, rapid advances after breakthrough. Any structure built for American forces needed to be temporary, portable, and quick to erect. The Quonset hut embodied this philosophy perfectly. On March 24, 1941, when the George A. Fuller Company received orders to design a revolutionary prefabricated shelter, the specifications seemed impossible. The Navy needed buildings that untrained soldiers could assemble in a single day using only hand tools, structures light enough to ship anywhere, yet strong enough to survive hurricanes and typhoons, shelters that could function in temperatures from 60 degrees below zero to 120 degrees above. The Fuller Company had 60 days to design the structure, build a factory, and begin production. Traditional construction methods could never meet such requirements. The solution required completely reimagining what a building could be. The design team studied the British Nissen hut as a starting point. Developed during World War I by Lieutenant Colonel Peter Nissen, the Nissen hut had proven adequate for basic shelter. Its semicircular corrugated steel shell provided reasonable protection and could be assembled by 6 men in approximately 4 hours, under ideal conditions. But the American team recognized critical limitations. The Nissen hut relied on an internal framework of steel ribs connected by bolts. Assembly required drilling precisely aligned holes and securing dozens of individual fasteners. The corrugated panels attached to wooden purlins using hook bolts. Straining wires had to be carefully tensioned to prevent the structure from spreading. Weather affected assembly. Rain made steel slippery. Cold numbed fingers. An inexperienced crew might need 8 hours or more. The Fuller Company engineers made a revolutionary decision. They would eliminate the complexity from field assembly by moving it to the factory. The structure would arrive at the construction site already broken down into foolproof components. Assembly would require no specialized skills, no particular expertise, just basic ability to follow simple instructions and drive nails. The key innovation lay in the steel ribs themselves. Instead of simple T-shaped sections requiring bolt connections, American engineers designed ribs formed from 2 steel channels welded back to back. The welds intentionally left narrow gaps shaped like a stretched-out letter W. These serpentine grooves allowed workers to drive hardened nails directly through corrugated panels into the steel ribs. The W-shaped channels gripped nails more tightly than wood. This seemingly minor detail revolutionized assembly. No drilling required, no bolt alignment needed, no specialized fasteners. Just ordinary hammers driving ordinary nails into grooved steel. If a worker could pound a nail, they could build a Quonset hut. The design incorporated other simplifications. The floor system used tongue and groove plywood that interlocked without fasteners. End walls arrived pre-assembled with doors and windows already installed. Corrugated panels shipped in nested stacks requiring minimal space. Instructions used simple diagrams showing each step visually. By June 1941, the first Quonset huts rolled off the production line. Assembly procedures proved remarkably straightforward. Lay out the floor framework and install plywood flooring. Position and bolt the steel rib sections together. Stand the ribs upright and bolt them to the floor framework at 6-foot intervals. Install the nailing strips between ribs. Nail the corrugated steel panels to the ribs starting at the ridge and working down. Install the interior lining. Attach the pre-assembled end walls. Connect doors, windows, and ventilation systems. A 10-man crew with hammers, wrenches, and basic hand tools could complete the entire process in 8 to 10 hours. One day. No cranes required. No welding equipment. No concrete mixing. No weeks of waiting for materials to cure. Just soldiers following printed instructions and driving nails into grooved steel. The contrast with German construction methods could not have been more stark, where German bunkers required specialized engineering knowledge, skilled concrete workers, and elaborate formwork. The Quonset hut needed only muscle and determination. Where bunkers demanded weeks of careful material curing, Quonsets were ready for occupancy as soon as assembly finished. Where bunker construction consumed scarce steel and cement, Quonsets used relatively modest amounts of materials that could be mass-produced. The difference extended beyond mere construction speed. German bunkers were permanent installations. Once built, they could not be moved. If military strategy changed and forces needed to redeploy, The bunkers remained behind, representing substantial investment in resources and labour that could no longer contribute to the war effort. Quonset huts, in contrast, were designed for impermanence. When American forces needed to relocate, crews could disassemble Quonsets almost as quickly as they had erected them. The structures loaded back onto ships and moved to the next objective. The same materials served multiple purposes in multiple locations throughout the war. Production scale magnified these advantages. Between 1941 and 1945, the United States manufactured between 150,000 and 170,000 Quonset huts in all variations. Taking the midpoint of 160,000, that represents approximately 308 huts per week, 44 per day, nearly 2 per hour every hour around the clock for 4 years. Germany, despite starting construction of the Atlantic Wall in 1942, completed approximately 25,000 bunkers by D-Day in June 1944. This represented 2 years of construction by Organisation Todt, employing up to 500,000 workers at peak. The Americans outproduced German fortification construction by a factor of 6, while simultaneously building Liberty ships, aircraft, tanks, and every other implement of war. The philosophical implications ran deeper than numbers. German defensive strategy assumed that the war would be won or lost at prepared positions. Massive fortifications would make invasion impossibly costly. Allied forces would batter themselves against concrete and steel until their resolve broke. This strategy required bunkers strong enough to survive sustained bombardment, hence the 2-meter walls, the elaborate ventilation systems, the carefully specified construction strengths. American offensive strategy assumed constant movement. Forces would land, establish beachheads, push inland, and keep advancing. Shelters needed only to protect troops from weather and provide functional workspace. They did not need to survive artillery bombardment because American doctrine called for air superiority and rapid advance that would put friendly forces beyond enemy artillery range. This distinction shaped every aspect of design. German bunkers included gas locks and chemical filtration because they anticipated fighting from fixed positions where enemy forces might employ gas attacks. Quonset huts had no such protection because American forces expected to be constantly on the move, making persistent gas attacks impractical for the enemy. German bunkers featured firing slits and protective embrasures because defenders needed to fight from within the fortification. Quonsets had simple doors and windows because they served as rear area facilities, not front-line fighting positions. If combat reached a Quonset hut location, American doctrine called for withdrawal to new positions rather than static defense. By February 1944, when Oberst Kestner watched concrete being poured into yet another Atlantic Wall bunker, the contest between these two philosophies had already been decided. The Germans simply did not realize it yet. The mathematics of force projection made the outcome inevitable. Germany was attempting to defend 5,000 kilometers of coastline with 25,000 bunkers. This meant 1 bunker every 100 meters on average. But bunkers could not move. They defended only their immediate location. An attacking force needed only to find the gaps between strong points, bypass the bunkers, and continue inland. American Quonset huts, in contrast, went wherever American forces went. When Allied troops landed at Normandy on June 6, 1944, cargo ships carried disassembled Quonsets in their holds. Within days of securing the beaches, Navy construction battalions were erecting Quonsets to house expanding operations. Within weeks, Normandy transformed from battlefield to massive military base, with Quonsets providing hospitals, supply depots, maintenance facilities, and barracks. The German bunkers at the beaches fought bravely but futilely. Naval guns and aerial bombardment suppressed many positions before infantry assaulted. Those bunkers that survived the initial bombardment became isolated strongpoints as Allied forces flowed around them. Within days, most Atlantic wall bunkers at Normandy had been captured or bypassed. The months of construction, the tons of concrete and steel, the elaborate defensive preparations, all rendered irrelevant by an attacker who simply went around them. Meanwhile, Quonset huts multiplied across the beachhead. Each one represented less than a day of labor to erect. Each one supported operations that pushed the front farther inland. The speed differential that seemed merely interesting in abstract comparison became strategically decisive in practice. The story of construction speed differences tells only part of the larger narrative. To understand why American Quonset huts could deploy in one day while German bunkers required 6 weeks, one must examine the entire industrial and logistical systems that produced these structures. German bunker construction depended on Organisation Todt, a massive paramilitary engineering organization created in 1933. Named after its founder, engineer Fritz Todt, the organization had overseen construction of the Autobahn highway system and the Siegfried Line. By 1942, Organisation Todt had expanded into occupied territories across Europe, managing construction projects from Norway to Greece. The organization operated through a complex contracting system. Organisation Todt provided overall management, engineering expertise, and labor allocation. They contracted with German and occupied country construction firms to undertake actual building work. These contractors received equipment, supervisors, and workers from Organisation Todt. Labor came in distinct categories. At the top were skilled volunteers, engineers, designers, and supervisors. These men received good pay and comfortable treatment. They provided essential expertise that kept projects on schedule and to specification. Below them came volunteer workers, often skilled technicians such as carpenters, plumbers, electricians, and metal workers. These workers also received wages, took holidays, and worked under reasonable conditions. But the vast majority of labor came from compulsory sources. Prisoners of war from Poland, France, the Soviet Union, and other conquered nations worked under guard. Workers from occupied territories were conscripted through forced labor programs. As the war progressed and German casualties mounted, even German civilians unfit for military service found themselves drafted into Organisation Todt projects. Conditions for forced labourers ranged from harsh to brutal. They received minimal food, inadequate shelter, and punishing work schedules. Sabotage attempts occurred regularly despite the risk of summary execution. Some workers mixed sugar or other substances into concrete batches, weakening the final structure. Others deliberately botched construction details. Such resistance was dangerous and often fatal, but it reflected the desperation of men working under compulsion. The sheer scale of Organisation Todt operations strained German resources. At peak activity in 1943 and 1944, approximately 1.4 million labourers worked on Atlantic Wall construction. Managing this workforce required extensive administrative apparatus. Daily, weekly, and monthly reports tracked progress, material usage, labour hours, weather delays, equipment inventory, staffing levels, and problems encountered. Every aspect of construction generated paperwork that flowed upward through Organisation Todt hierarchy. Material supply presented constant challenges. Concrete production required cement, sand, aggregate, and water in specific proportions. In 1942, Germany imported these materials from across occupied Europe. Cement came from Poland and eastern Germany. High-quality aggregate arrived by rail from distant quarries. By 1944, Allied bombing had disrupted transportation networks. Coastal batteries often used local beach sand and crushed seashells as aggregate substitutes, producing concrete of inferior quality. Steel reinforcement competed with tank and aircraft production for limited supplies. Germany's total annual steel production could not simultaneously support shipbuilding, armour manufacturing, weapon production, and fortification construction at required scales. Every ton of rebar embedded in bunker walls represented a ton unavailable for tank armour or artillery barrels. Transportation bottlenecks multiplied as the war progressed. Moving 60 cubic metres of concrete materials to a coastal construction site required extensive rail capacity. A single medium-sized bunker consumed materials equivalent to several railroad cars. With thousands of bunkers under simultaneous construction, Organisation TOT strained the French rail system to capacity. Allied air raids on marshalling yards and rail lines further degraded transportation efficiency. Weather imposed additional constraints. Concrete poured in freezing temperatures failed to cure properly. Winter construction in northern France, Belgium, and the Netherlands often halted completely from December through February. Spring rains turned construction sites into muddy quagmires. Summer brought optimal conditions, but also increased vulnerability to Allied air reconnaissance and bombing. Coastal construction sites stood exposed to observation from the sea and air, making them prime targets for attacks. Despite these difficulties, Organisation TOT achieved remarkable results given available resources. The 25,000 bunkers completed by D-Day represented an extraordinary construction effort. German engineering expertise produced fortifications of genuine strength. Bunkers built to proper specifications could indeed withstand tremendous punishment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But quantity alone could not overcome strategic limitations. The fundamental problem was that bunkers defended only their immediate location. An attacker, choosing a different landing site, rendered bunkers elsewhere useless. German intelligence struggled to predict where invasion would occur. The Pas-de-Calais region, opposite England, received priority fortification because it offered the shortest channel crossing. Normandy received less attention because it seemed a less likely target. This geographic guessing game meant that German defensive preparations were always incomplete somewhere. No matter how many bunkers Organisation TOT completed, gaps remained. The Atlantic Wall never achieved the continuous fortified barrier that propaganda claimed. It consisted of strongpoints separated by lightly defended stretches of coast. Meanwhile, American Quonset hut production followed entirely different organizational principles. The United States approached wartime manufacturing with ruthless focus on efficiency and scale. Rather than relying on skilled craftsmen working at individual sites, American industry created centralized production facilities that mass-produced standardized components. Strand Steel Division of Great Lakes Steel Corporation took over primary Quonset production in late 1941. The company operated massive factories in Detroit with multiple production lines running simultaneously. Steel coils arrived by rail from integrated steel mills. Automated stamping dies formed the coils into channels. Cutting machinery trimmed channels to precise lengths. Welding stations paired channels and tack welded them to create grooved ribs. Drilling equipment added bolt holes at specified locations. The entire process resembled automobile manufacturing more than traditional construction. Each component moved along an assembly line, where specialized equipment performed specific operations. Quality control happened through statistical sampling rather than individual inspection. If one component in 1,000 showed defects, engineers traced the problem to its source and corrected the manufacturing process. Corrugated panels came from specialized rolling mills that could form curved sections to exact specifications. Anderson Sheet Metal Company of Providence, Rhode Island, developed custom equipment specifically for Quonset panel production. The machines accepted flat galvanized steel sheets, passed them through progressive forming dies, and output curved corrugated sections ready for shipment. Plywood for floors and end walls came from lumber mills in the Pacific Northwest and Canada. Massive timber resources allowed continuous production without material shortages. Sawmills cut logs into veneers. Glue presses bonded veneers into plywood sheets. Cutting saws trimmed sheets to specified dimensions for Quonset components. Doors, windows, and hardware came from existing suppliers already producing similar items for civilian construction. The Quonset hut design deliberately used standard components wherever possible. This avoided creating bottlenecks from specialized parts that only one manufacturer could produce. If demand exceeded one supplier's capacity, additional suppliers could be brought online quickly. Packaging received careful attention. Early Quonset shipments required 12 wooden crates, totaling 3,212 pounds empty. Within months, improved packing methods reduced this to just 3 crates. The reduction saved shipping space and reduced handling time at both loading and destination. Every cubic foot saved in shipping meant more cargo capacity for other supplies. Transportation efficiency mattered enormously. The United States had to project military power across 2 oceans simultaneously. Every cargo ship voyage represented precious capacity. If Quonset components could ship in 3 crates instead of 12, the same ship could carry 4 times as many huts. This multiplication of effectiveness occurred at every stage of the supply chain. Consider the comparative shipping requirements. A German bunker could not ship at all. It existed only where constructed. All materials had to arrive at the construction site. If that site became inaccessible due to enemy action, the partially completed bunker represented total loss. A Quonset hut, fully disassembled, required approximately 270 to 325 cubic feet of shipping space. This was less volume than canvas tents with wooden frames required, yet the completed Quonset provided 960 square feet of floor space, weather protection equivalent to permanent buildings, and structural strength sufficient to survive hurricane-force winds. Loading and unloading operations favored Quonsets dramatically. Stevedores could handle crated components using standard cargo handling equipment, no special lifting gear required, no delicate positioning, just ordinary cargo operations moving standardized crates from ship to shore to truck to construction site. Navy construction battalions, the famous Seabees, became masters of rapid Quonset deployment. These units recruited men based on construction experience rather than physical fitness. Carpenters, electricians, plumbers, equipment operators, men often too old for regular combat service, but possessing practical skills invaluable for base construction. A typical Seabee battalion included about 1,000 men organized into companies with specific specializations. One company might handle earth-moving and site preparation. Another managed concrete work for foundations and roads. A third erected prefabricated buildings. This organization allowed simultaneous progress on multiple aspects of base construction. When a Seabee battalion landed on a newly captured island, operations began immediately. Bulldozers scraped jungle vegetation and leveled construction sites. Dump trucks hauled coral fill for foundations. While some crews prepared sites, others offloaded Quonset, crates from cargo ships. Assembly teams moved from site to site, erecting huts as soon as foundations were ready. The assembly process itself demonstrated American industrial thinking. Instructions broke the work into simple steps that required no special expertise. First, level the site and install foundation supports. For Pacific Islands, this often meant coral piers or steel platforms that elevated the structure above potential flooding. In areas with firm ground, simple concrete pads sufficed. Second, assemble the curved steel ribs and connect them with horizontal purlins for lateral stability. The ribs came in sections that bolted together using pre-drilled holes, no measuring required, no fitting, just matching numbered sections and tightening bolts. Third, raise the rib frames into position and bolt them to the foundation. Crews typically used manila rope and simple block and tackle systems to lift the arches. 10 men could raise a full rib frame into vertical position in minutes. Fourth, install the corrugated metal panels from bottom to top, driving nails through the corrugations into the grooved ribs. The serpentine slots in the ribs automatically aligned panels and gripped nails securely. Workers simply positioned each panel and hammered nails along the ribs. No precision required, no special skill, just repetitive hammering. Fifth, frame and install the end walls with their doors and windows. These arrived pre-assembled, requiring only positioning and bolting to the arch structure. Sixth, add interior finishing. The inner lining of masonite pressed wood nailed to the ribs just like the outer panels. Insulation fitted between the outer and inner layers. Flooring installed using tongue and groove plywood that locked together without fasteners. Finally, connect utilities as required. Some Quonsets received electric lighting powered by portable generators. Others remained unlit. Heating in cold climates came from portable oil stoves. Ventilation in tropical heat came from screened openings and natural airflow. The basic structure supported whatever modifications local conditions required. Experienced CB crews could complete this entire process in 8 to 10 hours. First-time crews might need 12 hours, but even the slowest crew finished within a single day. By the next morning, the structure was ready for occupancy. No waiting for concrete to cure, no complex systems to test and verify. Just immediate functional shelter. The strategic implications of this speed difference compounded over time. Consider operations at Guadalcanal, where American forces landed in August 1942. The initial assault captured a partially completed Japanese airfield. Within days, Seabees had finished the runway and begun erecting Quonsets for support facilities. Japanese forces still occupied portions of the island. Artillery, fire and air raids occurred regularly. Construction crews worked under sporadic enemy fire. Yet within weeks, Guadalcanal transformed from contested battlefield to functioning airbase. Quonset complexes provided maintenance hangars, supply warehouses, hospitals, barracks, and operations centers. Each Quonset represented less than a day of labor, but collectively, they created infrastructure that allowed sustained military operations. Aircraft based at Guadalcanal could patrol vast stretches of ocean, interdict Japanese shipping, and support further advances. The base that Quonsets made possible became the foundation for subsequent offensives throughout the Solomon Islands. Similar patterns repeated across the Pacific. At Tarawa, Saipan, Tinian, and dozens of other islands, Quonsets appeared within days of landing. American forces could establish functional bases faster than Japanese forces could mount effective counterattacks. This speed of deployment provided tempo advantage that Japanese defenders could not match. The contrast with German defensive construction became most stark when considering adaptation to changing circumstances. German bunkers, once built, could not relocate. If military strategy shifted and defenses needed strengthening elsewhere, new bunkers had to be constructed from scratch. Organization TOT could not simply move existing bunkers to new locations. Quonset huts, conversely, could be disassembled and relocated. When American strategy shifted from island to island across the Pacific, some Quonsets moved with advancing forces. Others remained at established bases that continued supporting operations. The flexibility to redeploy structures meant that investment in Quonsets retained value regardless of how strategy evolved. This flexibility extended to functional adaptation. A Quonset erected as a barracks could be converted to a warehouse by removing bunks and adding shelving. A warehouse could become a workshop by installing machinery. A workshop could transform into a hospital by adding partitions and medical equipment. The open, interior span and simple structure supported whatever purpose current needs required. German bunkers, by contrast, were purpose-built for specific functions. An artillery casemate could not easily convert to barracks. A personnel bunker poorly suited warehouse use. The specialized design that made each Regelbau type effective for its intended purpose limited adaptability to other roles. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.